because this is a really good way to start the year, light into dark, and talking about eclipses, which we can actually see in the UK, which would be great. Ian Ridpath really doesn't need much of an introduction to you. He's well known around the RAS and has done a lot of work, and indeed it wasn't until a few years ago that I realized that my Norton star atlas was epoch 1950 and needed updating, so I've got the 2000, but he's already working on 2050, isn't that right? No, not yet? Anyway, not that far ahead, but I mean, you know, don't worry. Anyway, give a big hand for Ian Ridpath.
Okay. Well, thank you, Marcus, and welcome everybody. Thanks for giving up your lunch hour to come in here. Well, eclipses, yes. I'm sure you all know there are two sorts of eclipses. There are eclipses of the sun on the left and eclipses of the moon, which we see on the right of the slide, and they occur in different ways. And what I'm going to do in the next 45 minutes or so is try to explain how eclipses occur, what they look like, what you're likely to see, and give you some hints on how to observe them, particularly solar eclipses. And at the end, I will give you some more information about the solar eclipse that's happening visible from this country on March the 20th, which is the biggest solar eclipse we've had in this country since the big one of 1999. This one isn't going to be a total, but it's going to be a very big partial. And actually, we also have an eclipse, total eclipse of the moon later in the year, and I'll mention that as well, but that's not for until September. Now, as I'm sure you all know, a solar eclipse happens when the sun is obscured by the moon, and a lunar eclipse happens when the moon enters the Earth's shadow and is darkened. And now, total eclipses of the sun are by far the more spectacular, they're the more scientifically interesting and important, and they're the ones that people travel all around the world to see. So I'm going to start with those. And I've got a little simulation here of what a total eclipse looks like. And this is very much speeded up. In reality, it takes an hour for the moon to completely cover the sun, or even over an hour to completely cover the sun, but I've compressed it into 20 seconds. And the moon starts by taking a little bite out of the sun, which gradually gets bigger. And by the time the sun is half covered, you start to notice the sky getting darker. It's not really until the sun is half covered that you start to notice it's getting darker. And then the sun becomes a crescent which gradually shrinks until it's completely covered. And this is what the sun looks like when it's totally eclipsed. All the bright disk is blocked off, and you can see the faint halo of gas called the corona around the sun, which is normally swamped by the sun's glare. And you can understand why ancient people were terrified by these things. I mean, I actually really realized the visceral fear when I saw my first totality in 1999. And you know, because the sun has been progressively vanishing for over an hour, and now it's gone completely. And you're standing there in the cold and the dark, and you're shivering and you're fearful, wondering if it's ever going to come back. But come back it does, as the moon moves on, and everything's back to normal about 3 hours after it all started. Now, the total part of the eclipse, when the sun is completely blocked out, can in theory last for up to 7.5 minutes at maximum. But in practice, it's usually just more like 2, 3, or 4 minutes. And eclipse enthusiasts travel all over the world just to see those precious few minutes of totality. And of course, they have to hope that it's not cloudy when they get there. And the fact that we get beautiful total eclipses like this is the result of a remarkable coincidence. The sun is actually 400 times larger than the moon. And here they are to scale, with the moon at the top, part of the sun at the bottom. But the sun is also 400 times farther away than the moon. So they appear almost exactly the same size in the sky. And it's one of those incredible coincidences of nature. If you're on another planet, you wouldn't get eclipses like we do on Earth. For example, imagine you were on Mars. And what you're going to see here is an actual sequence of Phobos, the larger of the two moons of Mars, moving across the face of the Sun, and it was taken from the surface of Mars by the NASA rover Curiosity. And Phobos is much smaller than our own moon, and it's closer in, so it moves much more quickly. And in fact, this is real time. It's all over in just over 30 seconds. And you can very clearly see that Phobos is irregular in shape. It's so small, it's not a rounded body. So this is as close as you're ever going to get to a total eclipse on Mars. So what circumstances are required for us to see an eclipse of the Sun from Earth? Well, the geometry of this is actually a bit tricky, but I've got a few diagrams here which I hope will help explain it. And we start with the Moon going around the Earth. And the Moon orbits the Earth once a month, and as it does so, it goes through its familiar cycle of phases. And this is a diagram as seen from above. Imagine we're looking down from above the Earth's North Pole. Now, solar eclipses can only occur when the Moon is directly between us and the Sun, which is the time that's called new moon. So you might be looking at this and asking, why isn't there a solar eclipse at every new moon? From this diagram, it looks as though the Moon ought to pass in front of the Sun on every orbit around the Earth. But if we look at it from side on, we can see that the Moon's orbit is tilted relative to the Earth's orbit. So on most occasions, the new moon either passes above the Sun or below it. And this happens during the daytime, so you won't even notice that the moon's there. And it's only when new moon occurs near the point where the orbits cross that you get an eclipse of the Sun. And this crossing point is called a node, and you hear a lot about nodes when dealing with eclipses. So to sum it up, the Earth, the Moon and the Sun have to line up in just the right way to cause an eclipse, and it doesn't happen all that often. Now what the previous diagrams didn't show is that the Moon casts a shadow in space. Now normally we don't notice this shadow because it doesn't fall on anything. But at the time of a solar eclipse, the Moon's shadow falls on the Earth and on you if you happen to be in the right place. So when you see a solar eclipse, you're actually in the shadow of the Moon. And like all shadows, it has a dark inner part called the umbra and a lighter outer part called the penumbra. And when you're inside the central part, the umbra, you see a total eclipse. And when you're inside the outer part, the penumbra, you see a partial eclipse. So to see an eclipse of the Sun, you have to be inside the Moon's shadow. And whether you see a total eclipse or only a partial depends whereabouts in the shadow that you're standing. Now let's have a look at the track of the Moon's shadow over the Earth. This isn't a real eclipse, it's just an imaginary example that I've drawn for demonstration purposes. And I've shown the track of totality in black, and you can see that it's actually quite narrow. That's why total eclipses are very rare from any one place. The chances of that band falling exactly where you are very small. On the other hand, the penumbra, which is the lighter grey area, is much wider, so partial eclipses are visible over a much larger area than total ones. And I've got some little simulations of what you'd see if you were at various different places within that shadow. If you're in the outskirts of the penumbra, and I've chosen London here just as an example, you'll see only a small partial eclipse like this. In fact, unless you knew it was happening, you wouldn't even notice anything. Now, if you're much deeper into the penumbra, where the two red pins are, for example, you'd see the Sun about half covered at maximum, like this. And it's only when the Sun is at least half covered that you start to notice the sky get dark. Anything less than 50% and the eye just adjusts to the change in light, and you don't notice it. But if you were close to the edge of the umbra, say down there where that red pin is, you'd see a very large partial eclipse like this. And when that much of the Sun is eclipsed, the sky does get noticeably darker, like twilight, and you'd also feel the air getting colder and clammier, and it's a very eerie effect. But to see totality, you have to be within that central dark umbra itself. And the closer you get to the exact centre of it, the longer the eclipse will be. And even then, as I've said, it's not going to last more than a few minutes. So that's the theory, and the geometry can get rather complicated when you go into it in detail. But what I'm sure what you really want to know is what this all looks like in practice. What can you expect to see? Well, one thing that becomes apparent at a solar eclipse is that the edge of the moon is actually quite mountainous. And some of these mountains go up to 14,000 feet or more, the height of the Matterhorn. And you can see these mountains during an eclipse. They give the moon a serrated edge, which you might just be able to see on this picture, which is a real photograph of an eclipse. And the dark patch on the sun at the top is a sunspot, and you can expect to see those as well. So because the moon has an irregular edge, the start of totality isn't instantaneous. Just before totality, some chinks of sunlight shine through the gaps between the mountains to form bright droplets that are known as BAILY'S beads, and they're also seen at the end of totality as well. And here's BAILY'S beads seen at an eclipse in China in 2008. And why are they called BAILY'S beads? Well, they take their name from Francis Baily, an English astronomer who was one of the founders of the RAS. And he first described these at an eclipse he saw from Scotland in 1836. They've been seen before, of course, but because they appear at virtually every eclipse, so he didn't discover them, but he was the first to describe them in any detail. And this painting may well look familiar to a lot of you because it's the one that hangs over the mantelpiece in the RAS library. And sometimes one of these beads is very much brighter than the others and creates what's called the diamond ring, which is very striking and beautiful. And like BAILY'S beads, you can see the diamond ring both at the beginning and the end of totality. And this is a triple image in which the photographer has caught the diamond ring both at the start of the eclipse and afterwards very nicely, with the fully eclipsed sun in the middle. And he's put them together into this rather nice composite. Now, if ever you're lucky enough to see a total eclipse, what should you be looking out for during those few minutes when the sun is totally obscured? Well, one thing is a layer of red gas above the surface of the sun. And this is called the chromosphere, from the Greek chromo, meaning colour. In other words, the name actually means colour sphere. And it appears red because it's composed of hydrogen, and hydrogen emits strongly at red wavelengths. And this is the chromosphere seen at the eclipse of 1999, the one that went across Cornwall, although in Cornwall it was cloudy, and this picture was taken in France. And as well as the chromosphere, you can see what appear to be bright red flames jutting many thousands of kilometres into space. And these are clouds of hot gas called prominences. And you can think of them as being an extension of the chromosphere. Now I'm going to show you a close-up of the area in the white box. And you can see that the prominences at the top, or the prominence at the top right, has detached itself and is moving off into space. And this picture gives you some idea of the incredible complexity of the gases swirling above the sun's surface. And solar physicists spend their entire lives trying to make sense out of what's going on here. And as you probably know, there are several satellites dedicated to observing the sun and its outer layers. But the main thing that everyone comes to see at total eclipse is the corona. And you can think of this as being the sun's outer atmosphere. Although, unlike the atmosphere of the Earth, it's not cold, but it's very hot. It's a couple of million degrees. And you can think of it as gas boiled off from the surface of the sun, and the gas keeps on streaming outwards to form the solar wind of particles that flows past the Earth. Now, because the corona is so faint, you can only see it when the sun's disk is totally blocked out. You don't see it at a partial eclipse at all, just a total. And then it shines with a beautiful pearly white light, and it really is the sun's crowning glory. Now, the shape of the corona changes with solar activity. I'm sure you all know the sun goes through a cycle of activity that lasts roughly 11 years, and the shape of the corona changes with it. And here's the corona around the time of maximum solar activity. and you can see streamers of gas coming off from all around the sun. And they give it the appearance of a giant sunflower. Now here's the corona at solar minimum, and you can see it's quite different. It's much more irregular. There are long plumes of gas coming off from near the equator, but there are big gaps near the poles. And if I put the two images side by side, the differences should be quite obvious. And all these shapes and structures are governed by the sun's magnetic field, which is much more complicated than the Earth's magnetic field, and it changes during the solar cycle. So the overall shape of the corona will depend whether it's solar maximum or solar minimum or somewhere in between. And if you can tear your eyes away from the sun and look around you just before or after totality, you can see the moon's shadow either approaching or receding like a great storm cloud. And here's a still image of a total eclipse, and I think you can see that there's a dark cone with the edges falling roughly here along the orange lines. And that's the shadow of the moon falling on the Earth and falling on you as well if you're inside it. And you feel a bit like you're inside the shadow of some giant predator hovering above you. Now here's a movie clip taken at an eclipse in Australia in 2012 by an Australian photographer called Colin Legg, who's kindly allowed me to show it to you. And he was up on a mountainside, and from there he got a particularly good view of the moon's shadow sweeping across the sky. And the sun's at the right of centre, much overexposed in that orange ring, and ignore the bright blob to the left of it, which is just a lens flare. And the total eclipse lasted just over 2 minutes, but he speeded it up to about 10 times faster than in real life, so it only lasts about 12 seconds in this clip. And the moon shadow comes in from the left. And the sun's now totally eclipsed. You can see the corona around it. And notice how red and thundery the sky is in the partially eclipsed area on the horizon. And then the shadow sweeps away, and the sun is back. And here's the eclipse again from a camera with a slightly wider field of view. And again, of course, that's very much speeded up. Now, something else to look out for during totality is bright stars and planets. The sky gets so dark that you can actually see stars and planets quite close to the sun. And here's some eclipse watchers down there at the bottom of the picture. And there's the totally eclipsed sun up in the sky. But above left of the sun, can you see these two bright spots? They're not flaws in the image. They're actually the planets Mercury and Venus. So bright planets are something else to look out for in the dark skies during totality. In fact, we might be able to see Venus and possibly even Mercury at the eclipse on March the 20th, and I'll show you a diagram at the end. Now, I said earlier that the moon and the sun appear almost exactly the same size in the sky, but there are times when they don't. And that's because the moon's orbit is elliptical. Its distance from us changes by about 15,000 miles in each direction, and its apparent size changes with it. And the difference is so small that normally you'd never notice, but you can tell the difference at eclipses. And if I bring in the moon to its closest to Earth, we find that it's about 6% larger than average. And that means that we'll have a longer than average eclipse. The longest eclipses occur when the moon is near its closest point to the Earth. But if I now move the moon away to its most distant point from the Earth, it's now 6% smaller than average. And at those times, it's no longer big enough to cover the sun. It doesn't fit. So when the moon is at its farthest point from the Earth, we get a very special sort of eclipse called an annular eclipse. And the name comes from the Latin word annulus, meaning a ring, not because they happen every year. And here's an animation of what an annular eclipse looks like. Now again, this is very much speeded up. The whole thing takes a few hours, as with any other solar eclipse. But this time, even at mid-eclipse, the sun isn't completely covered. There's a ring of sunlight left around the moon, and this is bright enough to swamp the faint light from the corona. So at an annular eclipse, you don't see the corona, you don't see prominences, and the sky doesn't get as dark as at a normal total. but it does produce some spectacular results. Here's an example. It's an annular eclipse photographed just before sunset in New Mexico in 2012. And the sun, being low down, is filtered by the atmosphere, and the ring is quite easily seen, even without any special optical equipment. And at this eclipse, the sun is so low down that the shape of the ring has been distorted by the atmosphere, so it looks squashed. And the intervention of some palm trees makes for a nice picture. This was taken from near San Diego. I'm going to talk now about ways of observing solar eclipses. And what I'm going to say also applies to observing the sun in general. And it has to be done with great care because the sun is dangerous to look at. When you were at school, did you ever focus the sun's light onto some paper or dry leaves with a magnifying glass? Or a spider, if you were a really nasty little boy. And do you remember what happened to them? Well, imagine focusing the sun's light not onto the paper, but onto your eyes. Now, that's what binoculars and telescopes would do. And I think you can imagine what damage you'd do to your eyes. You'd blind yourself immediately. So please never, ever look directly at the sun through binoculars or a telescope. Even simply staring at the sun for long periods can damage your eyes. If you've ever glanced at the sun for more than a few seconds, you'll probably remember the after images that you get in your eye. Well, if you stare for long enough, those after images will be burnt into your retina, and you may have permanent damage. Sunglasses don't provide sufficient protection, nor do old pieces of photographic film. A welder's glass is okay, if you happen to know a welder, but the best way to observe the sun with a telescope is to project the image. Of course, this is how solar observers look at sunspots all the time. Now, you can buy expensive filters to put over the front of the telescope, but projection is simple and cheap, and it allows several people to watch at the same time. You can also do the same thing with binoculars, and in this case, you get 2 images instead of 1. And it's better if you have a tripod and you can fit some cardboard over the front to create a shade. And as you can see, you don't need anything sophisticated. Now, you'll find a lot of stuff on the internet about using a pinhole camera to project an image of the sun, whether partially eclipsed or not. And this lady's using a piece of paper with a pinhole in it, and you can find instructions for making a pinhole camera from a shoebox with the hole at one end and using the other end as a screen. But you don't need to go to all that trouble. Reach for something that's already got a hole in it, or even several holes in it. You can use a colander or a strainer of some kind. A simple straining spoon with holes in it can work, and you'll get multiple images of the eclipse. And if you haven't got any of those things handy, you can make a pinhole with your fist, or even crisscross your fingers to make a lattice work of them. And you might be lucky enough to find some natural pinhole cameras. Gaps between leaves on trees and bushes make pinhole cameras, and the images fall on the ground or sometimes on the side of a building, as here. And the wind blowing and moving the branches around produces some quite beautiful effects. Now, you need quite a big garage, and this is actually a garage door in California, so only in America. But of course, for the March eclipse, you'll need to find some evergreens. There won't be that many leaves on the trees in March. But you need a very bright, strong sun for pinhole cameras to work, and the image is usually pretty lousy. Now, on March the 20th, the sun will be less than 30 degrees altitude at mid-eclipse, and there's bound to be cloud around as well. So I don't think pinhole cameras are actually going to work terribly well for you. So best of all are special eclipse glasses, which are made of a simple piece of cardboard with specially coated plastic lenses that filter out almost all the sun's light and heat, so you can watch the sun quite safely. And you can buy these glasses online, and they cost only a few pounds, and you can use them for watching sunspots as well. Just Google eclipse glasses. And they're cheap enough that you can buy 2 or 3, and they can be used by all the family. I'm going to move on now to lunar eclipses. And these are less spectacular than solar ones, but they're a lot safer to observe. You can look at them with binoculars, telescopes, whatever you like. Now, I suppose it goes without saying that whereas solar eclipses occur during the day, lunar eclipses occur at night. And unlike solar eclipses, you don't have to be in a special place to see them. You can see lunar eclipses from anywhere on Earth that the moon is above the horizon. If you can see the moon, you can see the eclipse. And at a lunar eclipse, the moon enters the shadow of the Earth. And this can happen only at full moon, when the moon is on the opposite side of the Earth from the sun. So during the eclipse, the full moon turns dark. Now, there isn't a lunar eclipse at every full moon, because if you remember the diagram earlier, the moon's orbit is tilted, so at most full moons it passes either above or below the Earth's shadow. And like all shadows, the Earth's shadow has two parts to it, the inner darkest part called the umbra, and a lighter outer part called the penumbra. And as you can see, the Earth's shadow is very much bigger than the moon, which is up at the top right there. Now we'll see what happens when the moon passes through the Earth's shadow. And again, this is very much speeded up, and the real thing can take well over 3 hours, but I've compressed it into 30 seconds. And when the moon enters the penumbra, there's hardly any dimming at all, and you wouldn't even notice this part of the eclipse was happening unless you knew in advance. It's only when the moon enters the umbra that it begins to darken noticeably, and when it's fully in the umbra, it usually turns a dark coppery red colour, and then it returns to normal as it leaves the shadow again. And totality can last for over an hour and a half, depending on how far the moon dips into the Earth's shadow. But the edges of the shadow are fuzzy, so there's no precise start or end to a lunar eclipse like there is with solar ones. And here's a sequence of 3 pictures showing the moon passing through the Earth's shadow at an eclipse. And I think this gives a very good impression of the size of the shadow relative to the moon, and you'll notice that the shadow is round, which proves that the Earth is round. And in fact, even ancient astronomers realized that the Earth was round from the shape of its shadow at lunar eclipses. Now, you might be looking at this and thinking, well, if the moon's totally eclipsed, how come it's still visible? You might expect it to go black, but as you can see from the middle image, it hasn't. It's turned orange. And the answer is that the Earth's shadow is not totally dark. Sunlight is refracted through the Earth's atmosphere and into the shadow. And as the light passes through the atmosphere, it becomes redder, in the same way that the sun is reddened at sunset. So the central part of the Earth's shadow isn't completely dark, and the moon doesn't usually vanish, even when it's supposedly totally eclipsed. Now, if we imagine this from the point of view of someone on the moon, what they'd be seeing is the sun being eclipsed by the Earth. And imagine you're on the moon looking up at the sky. There's the Earth at the upper right, you can just about see it, and you're looking at the night side of the Earth. And there's people down there looking up at the full moon, waiting to see it eclipsed. And as I run the simulation, you see the Earth covering the sun, and as it does so, the sun's light is refracted and reddened as it passes through the Earth's atmosphere. So you'd see the Earth surrounded by a red fringe. And here you're seeing the sun's light after it's been bent through the Earth's atmosphere. You can think of it as like being a 360-degree sunset. Unlike any sunset, the colour and the darkness of an eclipse depends on conditions in the Earth's atmosphere. If there are lots of clouds or dust from volcanic eruptions, much less light will get through and the eclipse will be dark. So literally, what we see at a lunar eclipse is affected by what's going on in the atmosphere above our heads on Earth. For example, there was a very dark lunar eclipse in 1992 following the eruption of Mount Pinatubo in the Philippines, which you might remember. And this pumped colossal amounts of dust and sulfur dioxide into the stratosphere, and sunsets were very red for a year or more after the eruption. And it produced a layer of haze several miles deep, which astronauts aboard the space shuttle photographed from orbit. It's this dark brown line below the clear air above. And here we're looking at it almost horizontally, so it appears particularly dark, and you can easily imagine this layer acting as a very effective filter on sunlight passing through it and causing a dark eclipse. There was a very dark lunar eclipse after the eruption of Krakatoa in 1883. Here's a drawing of a lunar eclipse in the year following the eruption, when the atmosphere was still very dirty. And here's one 4 years later when the dust had settled out. So it turns out that lunar eclipses are a very useful way of monitoring the clarity of the Earth's upper atmosphere. And the clarity of the atmosphere also affects the warming of our planet, which is, of course, a hot topic at present. Now, sometimes the outer edge of the umbra appears bluish. Now, the books don't usually tell you about this, but I think you can see the bluishness at the top of this picture, and I've seen it in eclipses myself. From what I read, this is caused by the ozone layer in the upper atmosphere, which apparently makes the light passing through it turn bluer rather than redder. So the Earth's shadow has a range of colours, from light blue at the edges through orange in the middle to dark red or brown at the centre, and they vary from eclipse to eclipse. And these various colour effects are one of the main things to look out for at a total lunar eclipse, even if it's only for aesthetic reasons rather than scientific ones. Well, here's a few facts and figures about lunar eclipses. There can be up to 3 lunar eclipses in a year, total or partial, but in some years there aren't any at all, and that compares with as many as 5 a year for solar eclipses. Each lunar eclipse is visible over a much wider area of Earth than a solar eclipse. In fact, you can see each one from more than half the Earth. And because of this wider area of visibility, you'll see twice as many lunar eclipses as solar ones from any given place. And the next total eclipse of the moon visible from the UK is in September this year, and I'll tell you more about that later. Now, certain eclipses have made history for one reason or another, and I've chosen some examples, or 4 examples, that I think are particularly interesting. And for the first of them, we go back to 1504, when it's said that Christopher Columbus used a lunar eclipse to scare the natives in Jamaica into helping him during his 4th and final voyage to the New World. Now, he was stuck on Jamaica because his ships were leaking and falling apart, and he was awaiting help, but it was a very long time in coming. And after about 6 months on the island, the sailors had become so unpopular that the locals refused to supply them with food anymore. So there he was, with no idea when help would arrive, and his crewmen starving and on the verge of mutiny. Well, Columbus had an almanac that told him a total eclipse of the moon was about to take place. So he tried a trick. He told the locals that if they didn't continue supplying his fleet, God would express his anger by causing the moon to change colour. Fortunately for Columbus, the prediction was correct. He'd have been in bad trouble if it had been wrong. And on the appointed night, the moon duly turned an angry red as it rose. And this display of apparent supernatural powers had a suitable effect on the locals, who resumed their supplies. And eventually Columbus and his crew were rescued and returned home. So that's Columbus saved by the total lunar eclipse of March 1504. And this idea of the Western explorer predicting an eclipse to scare the superstitious natives has been used in fiction as well, and the idea probably comes from this supposedly true story. Here's another eclipse story, the discovery of helium. Now, the sun is made mostly of hydrogen and helium, which are the 2 most common gases in the universe, but on Earth, helium is rare, and we didn't even know it existed until 1868. And it was first found at a total solar eclipse in that year. And these are the 2 men who were most closely involved in the discovery, a French astronomer called Jules Janssen and an Englishman called Norman Lockyer. And the eclipse of 1868 went across India and Southeast Asia. And Janssen observed it from a place called Guntur in the east of India. And he studied the light from the prominences with a device called a spectroscope, which splits up light into its component wavelengths. And he found a bright yellow line in the spectrum that didn't correspond to anything that was then known. Now, Lockyer wasn't at this eclipse. He was at home in London at the time. But he heard of the discovery of this feature, and he concluded that it must be due to a previously unknown element, which he named helium, from the Greek word helios, meaning sun. So helium was found on the sun before it was found on Earth, and it's got its name from the sun. And it's a gas that we're all now familiar with. It's what's in your party balloons. Well, an eclipse of the sun in 1919 was used to confirm one of the key predictions of Einstein's theory of relativity. And the prediction was that a beam of light would be bent when it passed through a strong gravitational field. Now, Einstein's theory was published in 1916, and one of the few people who understood the significance of it was this man, an English astrophysicist called Arthur Eddington. And he decided to test the theory by seeing if the light from stars was bent as it passed close to the sun. But how do you see stars when they're close to the sun? Well, you wait for a total solar eclipse. Unfortunately, Eddington didn't have to wait long, because there was one in May 1919 which went across the Atlantic. And Eddington set up 2 observing stations, one at Sobral in Brazil, where he sent some colleagues, and one at an island called Principe off the coast of Africa, where he went himself. And this is one of the plates they took. It's a negative, of course. And there are some very faint stars between these little tick marks, which you probably can't see, but which show up on the original plates. And Eddington compared the positions of these stars to their positions as measured without the sun in the way, and they had moved ever so slightly, as predicted by Einstein. So Einstein was right, and this was the first experimental confirmation of the theory of relativity. And this made not only Einstein famous, but also Eddington. And 15 years later, he received the ultimate accolade. Not the Nobel Prize, but the cover of Time magazine. Now, one of the problems with observing solar eclipses is that they're over so soon. And you can do something about that by trying to keep up with the moon's shadow, but you have to go very quickly. And what's the quickest you can go? Well, in 1973, a group of scientists from the UK, France, and the United States used a supersonic Concorde to fly along the path of totality. And it was a prototype Concorde, not one that was going to go into service, so they were allowed to cut windows in the roof for their instruments to look through. And there they are on top of the fuselage, cleaning those windows just before takeoff. And they were piloted by the famous Concorde test pilot, Andrei Turcar. And they bombed along the eclipse path at top speed for nearly 2,000 miles over Africa. And even at Mach 2, twice the speed of sound, they still weren't quite as fast as the moon's shadow, but they were able to extend totality to 74 minutes, nearly an hour and a quarter, which is 10 times longer than you'd ever see from the ground. And it's still the record duration for observing an eclipse, and by quite a long way. Okay, well, let me now summarize the main points that I've been talking about, and then I'll come on to some specific details about the upcoming eclipse in March. Firstly, solar eclipses. Solar eclipses happen when the moon passes in front of the sun, and this can only happen around the time of new moon. 2 to 5 solar eclipses occur each year, either partial or total. A solar eclipse can be seen only from within the area where the moon's shadow falls. The track of totality is very narrow, so you'll have to travel to the right place to see a total eclipse. Partial eclipses last for up to 3 hours, but totality is usually only a few minutes. At totality, you'll see the sun's corona and perhaps a few red-coloured prominences as well. And great care must be taken when observing the sun to prevent eye damage. And now the main points about lunar eclipses. They occur when the moon enters the Earth's shadow, which can happen only around the time of full moon. There are up to 3 a year, sometimes none. The average is 1 or 2 a year. They're visible from anywhere the moon is above the horizon, if it's clear. The moon doesn't usually vanish from view at a total eclipse, but it turns a coppery red. Total lunar eclipses can last for up to 1 hour and 40 minutes. And the colour and darkness of the eclipse moon depends on the clarity of the Earth's upper atmosphere. Okay, within the last 5 minutes or so, I'm going to look at specific details for the solar eclipse that we'll see, I hope, from the UK as a large partial on March the 20th. And this is the track of totality. It's the band bordered by the blue lines, and as you can see, it passes north and west of the British Isles, and the longest duration of totality is here, just north of the Faroe Islands, where it will last 2 minutes and 47 seconds. And here's a little animation of the moon shadow moving over the Earth. The sun's off to the right, and the moon shadow comes in from the left. And first of all, you'll see the lighter penumbra, the region of partial eclipse, and then the darker umbra comes in. And the umbra is passing between Britain and Iceland, and it's about to pass over the Faroe Islands. And you'll notice that it's very elongated because the shadow's falling obliquely on the Earth. It's so far north. And I'll run it on a little further. And now it's approaching the Arctic island of Svalbard, and the shadow is getting even more elongated. And as we run on to the end, we see that the shadow slips off the Earth over the North Pole. And I'll just run through that for you again without stopping. Over the Faroes, over Svalbard, and away. And there are ships going up there to see this. I suspect most of them are already fully booked, although I understand you might be able to get a place on the P&O Oriana if you're quick. And this is how it will look from various places in the UK. And as you can see, it will be a pretty big partial over the entire country. You're better off the further north and west you are. Up in Scotland, the sun will be down to a thin crescent, but even in the south, we'll see over 80% of the sun eclipsed. And that's the best since 1999. Now, these are the timings for the eclipse, but the basic message is that it starts just before 8:30 in the morning, and it's all over by coffee time, just over 2 hours later. Now, we'll still be on GMT, so you won't need to add an hour to these times. Of course, there'll be loads more detail in the press and online, and of course, Astronomy Now magazine and similar magazines. And the RAS is producing a leaflet about it too, which you'll be able to download from their website, so keep an eye on the website. Now, I've been wondering how dark the sky will get around the time of maximum eclipse, whether it'll be dark enough to see bright planets like Mercury, Venus, and Mars also is going to be there. Now, Venus will be easy enough because it's the brightest planet by far, and Mercury is to the right of the Sun, and you might be able to see that with the naked eye as well, particularly the further north you are, where the Sun is going to be over 90% eclipsed. But Mars you'll certainly need binoculars for, and of course you must be very careful that you don't accidentally look at the Sun through your binoculars. So that's something to look out for. It really does depend on the sky conditions. But you might see Venus with the naked eye during the partial eclipse. And as I mentioned, there's a total lunar eclipse this year as well. It's on September the 28th, although you'll have to stay up pretty late to see it. Totality doesn't start until 3 o'clock in the morning, and it lasts for well over an hour. So you'll only really be able to see this if you don't have to get up and go anywhere the following morning. And this one should appear quite light in colour because there haven't been any volcanic eruptions recently, unless one goes off before then. Now, as I mentioned, the RAS is producing a leaflet on the solar eclipse, which you'll be able to download from their website. It's not quite finished. I believe it's still in preparation. But in the meantime, if you want to know more about eclipses, you can do no better than go to the website of this man, Fred Espenak, who's one of the world's top experts. He runs his own pages under the title MrEclipse.com, and he's also responsible for NASA's own official eclipse pages, and I've given you the addresses of both of them there. And Fred's a great astrophotographer too, so if you want tips on photographing eclipses, which I haven't covered today, this is the place to go. The librarian, just before I close, the librarian has asked me to mention that she has put out a display of some eclipse pictures and books up in the RES library. So if you get a chance before you leave, do go over to the RES apartments and go up into the library and have a look at the little display we've got for you up there. That's, Chairman, all I have time for you. Oh, the Chairman's gone to sleep.
historical aspect of Columbus and Einstein.
Thank you.
Good.
Thank you. Okay, right. If you have any questions, we've got a roving mic here, so you have to wait.
Question, yes, first up there. Thank you.
From your early slide, I rather thought that you wouldn't... From one of your early slides, I rather thought that you wouldn't be able to ever see an eclipse from the North Pole because of the planes, but then you show us a picture where it is going virtually over the North Pole. So I'm obviously far too naive. Why was I wrong?
Well, I suppose because normally you only ever see pictures of eclipse tracks going across the central part of the Earth. They are unusual, but yes, I mean, theoretically it can happen, yes, and almost does in this case.
I mean, I would have thought that you would be far more likely to see eclipses if you lived on the equator. So is there sort of a probability in relation to latitude?
That's an interesting question. There very likely is, yes. I'm sure there is. I don't actually have any figures for you.
Thank you.
In one of your early pictures, you showed BAILY'S beads, but there was no corona in those pictures. Is the corona so faint that as soon as you've got BAILY'S beads, it disappears?
That's right, yes. I mean, even those little last few chinks of sunlight are so bright. I mean, it also depends on the exposure that the photographer gave it. Obviously, he's just exposing for the beads. So if you'd given a longer exposure, then you might have got something of the corona. But yes, I mean, even those last few little chinks of sunlight do blot out the corona. It is that faint. There's a lady down here.
Yes.
No, sorry, the lady behind you.
Sorry.
Yes, she had a hand up first.
Hopefully we get no cloud in London. I would like to observe the solar eclipse. Which is the better, white light or hydrogen alpha?
Oh, it's a technical question. It actually doesn't matter when it comes to an eclipse. Have you got one of those hydrogen alpha viewers? Yeah, yeah. It actually doesn't really matter when it comes to an eclipse.
Thank you.
Okay, Mr. Mater. Microphone.
Sorry. Could you confirm that Venus is the size of the Earth, but it has a much denser atmosphere?
I can confirm both those points, yes.
Yes. Sorry. Can I just say,
question,
they
Mr.
made
Speaker.
a discovery of 2 planets with Earth-like conditions in some other galaxy. I subscribe to the Times newspaper. I get it half price. It was in there.
Yes, they've found Earth-like planets around other stars, but they haven't found an Earth-like planet around a Sun-like star, and that's still the thing that's missing.
It's neither you. It's wishy-washy.
And it'd be difficult to see eclipses there.
Excuse me. I'm a member of the Flamsteed Astronomy Society based at Greenwich, and we with the observatory and I believe the BBC will be running an event on the 20th of March, starting from about 8 o'clock. We will be using various instruments from hydrogen alpha to white light to calcium K, and it is a public event, so if anyone wants to come up there, hopefully we won't have any cloud, you'll be more than welcome.
Okay, thank you for that. And is it live transmission on the BBC, or?
I understand, because I think Stargazing Live is also part of
Yeah.
Let me just ask, how many people have not ever seen a solar eclipse?
What, the total one?
No, any sort.
No, any sort.
Oh,
So everybody, just about everybody has seen one or other. And lunar, has everybody seen a lunar eclipse? Ah, well, experts, all of them. The question at the back there.
As we're in a maximum solar situation, are we likely to see the sunflower formation this time?
Well, that's what you would expect from those pictures. If we don't, then don't come and ask me for an explanation.
I want my
ask
money
a solar
back.
physicist. But yes, you would expect the corona to be more like that if you happen to be seeing the totality in March, yes. Because we are just past solar maximum by a year or so.
Will there be a kind of partial effect, say in London, to give that sunflower effect?
No, no, you won't see any of the corona. You have to be
Yeah.
in the path of totality.
You won't see any of that effect at all.
No.
Okay. This is a solar question, not an eclipse question. But you did mention it. Why is the corona so much hotter than the sun itself?
That is a very good question, which solar physicists have been spending an awful lot of time trying to answer, and no one actually knows the answer. It's totally counterintuitive. Yes. And if you come up with the answer, come along to an RES meeting and tell us. Oh, oh no, 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 he hasn't got a question. He's just going to plug his tickets, isn't he? No, I can't speak at Astrofest. I'm not going to be there, and John Mason is giving the talk instead.
I apologise if this might have been asked while I was out of the room for a second, but another one of your passion is the aurora. If you're up north, do you think there's any chance you will see a total eclipse with aurora in the sky as well?
It would be wonderful, wouldn't it? The problem with that is, I mean, theoretically it's possible. If there was a very bright aurora on the day of the total eclipse, people up in the Faroe Islands or along the path of totality could see a total eclipse and a bright aurora in the sky at the same time. It is possible. It's unlikely because the auroral oval, the area of permanent or main auroral activity, doesn't come as far south during the day. It spreads more on the night side of Earth. So that would be against it. But it is theoretically possible, and I will be awfully jealous if the people up there do see that.
I think that concludes. I'll just say that if you've enjoyed the lecture today, then tell the people, your friends who haven't been able to come, that you're talking at 6 o'clock tonight over in the RAS.
Yeah, and if you loved it so much, you want to hear it all over again. And if you missed anything, if you went to sleep at any time...
It's his fault, Fred Espinat. When I heard that, I dropped. Anyway, yeah, and if there's any question that you think of in the meantime, come back and see us and ask you.
Thank you.